Skill machines, temporal logic composition in reinforcement learning. This is joint work with Devon Jarvis, Stephen James, and Benjamin Rosman at the University of the Witwatersrand in South Africa. One of the main promises of reinforcement learning is to one day have generally capable robots that can solve many complex tasks in an environment. Consider, for example, this office great world. The robot may be required to solve several complex tasks where it needs to interact with several components like the rooms, coffee stations, decorations, mail room, and the office. A major challenge is, however, to specify tasks in a manner that is both interpretable and verifiable. Also, designing agents that can solve such tasks without having to do costly learning every single time a new task is presented. One common approach to specifying tasks is through reward machines, which are finite state machines that encode the task to be solved. Here, the edges are over expressions, over events in the environment, and with associated rewards. The robot is also equipped with a set of sensors that tells it which events currently hold true in the environment at that specific state. Here is, for example, the reward machine that specifies the task where the agent needs to deliver coffee to the office without breaking any decoration. This task can also be specified as the following LTL expression, and the reward machine can be generated from that LTL expression. So given tasks specified as reward machines, how do we solve them in an efficient way? That is, without having to do further learning every single time a new task is presented. To achieve this, we introduce skill machines, which are finite state machines that encode the solution to the task as the composition of primitive skills. To learn these primitive skills, the environment is first augmented with the terminating action, a goal space, and a set of constraints which represent the propositions that may be required to be forced during downstream tasks. The skills primitives are then learned in a reward machine free setting with a set of skills corresponding to each proposition in the environment. After learning these skill primitives, we can then plan over the reward machine to learn the skill machines. The planning can be done using any off-the-shelf algorithm like value iteration, for example. Doing value iteration over the reward machine, we obtain the value of each edge in the reward machine. We can then select the skill corresponding to the edge with the maximum value at each node. This gives us the skill machine for the corresponding reward machine. By then following the skill machine, acting greedily with respect to the composed value function at each node, the agent is able to successfully solve the task. In the case where the skills obtained from the skill machine is not optimal and optimality is desired, we can do additional learning on top of the skill machine to obtain optimal policies. To achieve this, we have a hyperparameter that values how much the new scale or the scale from the skill machine contributes in the behavior policy. In our experiments, this hyperparameter called beta is set to the discount factor. This pretty much guarantees that the scale from the value function from the skill machine won't overwhelm the value function for the scale for the current task which is being learned. As we see from the animation here, the agent effectively learns to change its behavior from the skill machine to a more optimal behavior, where it first goes to a coffee that is not the nearest coffee before going to the office. We run several experiments comparing skill machines with various baselines. We first consider the task where the agent needs to deliver coffee and mail to the office without breaking any decoration. While regular pure learning struggles to learn state-of-the-art methods like counterfactual reward machines and hierarchical reward machines start learning after about thousands of episodes, skill machines have near optimal performance from the beginning, as they leverage the composition of pre-trained skill primitives. Now consider a much harder task where the agent needs to deliver mail to the office until there is no mail left, then deliver coffee to the office while there are people in the office, then patrol rooms A, B, C, D, and back to A, and while doing all of this, never break any decoration. Here, despite the fact that pure learning and counterfactual reward machines are guaranteed to converge in the limit, they fail in practice because the probability of successfully finishing an episode is extremely small. We observe that only hierarchical reward machines are able to learn the task, while skill machines still outperforms it with near optimal performance from the start, again because of the composition of the pre-trained skill primitives. Finally, since any off-policy RL algorithm can be used to learn skill machines, we observe that they still perform extremely well even in function approximation scenarios where the agent receives very high dimensional pixel observations. As we can observe from the bar chart below, the composed policy is very close to the optimal policy, even without doing further learning. And as we showed in the previous experiments, the agent can use few-shot learning to learn optimal policies. In conclusion, we introduce skill machines, which is a framework that allows agents to solve extremely complex tasks involving temporal and concurrent composition. These skill machines can be learned directly from reward machines and are sufficient to solve tasks near optimally without further learning. Finally, we demonstrated that the optimal policies can always be obtained few-shot by using any off-the-shelf off-policy RL algorithm. We believe this is a step towards truly general reinforcement learning agents. Thank you.